For today's video, we are going to talk about conservation of energy. Conservation of energy says that energy is never created or destroyed, it can only change the form that it is in. So when we are looking at an isolated system, or a system which no external forces are acting on it, the total energy of the system will always stay the same, and that energy will only be able to convert into different forms. So we saw, looking at a mass attached to a spring, we saw how that total energy was always the same in the system. The energy just changed forms from elastic potential to kinetic, or from kinetic back to elastic potential. Conservation of energy says the energy which something starts with is the same as the energy which something ends with. So we can take a snapshot in the beginning, that's how much energy the system has in the beginning, and that energy will be equal to how much energy the system has at the end when we take a second snapshot. We can use energy equations to calculate many of the same things we use kinematic equations for. So we can calculate how high up a ball might go, or what the starting velocity, the ending velocity of a projectile is. Here at the bottom, we see a lot of different forms of energy, and basically this diagram is showing that energy is not created or destroyed, it can just convert into different forms. The conservation of energy equation says, as we said before, the starting energy, or E0, is equal to the final energy. So when there is no work done on the system, there's no change in energy. The initial energy and the final energy will be the same. Now, if there is work done on a system, there will be a change in energy, but we know how to account for that work. So we know the starting energy plus the work done will be equal to the final energy. Now that work done can be positive or negative, so the final energy can be greater or less than the starting energy. Problem solving with conservation of energy. Once you learn the technique to solve problems using conservation of energy, most of the problems will be pretty simple. So there's four main steps to solve problems using conservation of energy. First, let's look at what an example problem would look like. A rock of mass 10 kilograms is dropped from an initial height of 5 meters. How fast will it be traveling when it hits the ground? So the four steps involved are, first, to identify the types of energy. We only learned about 3 different types of energy, so we know it must be kinetic, gravitational potential, or elastic potential energy. We want to identify the beginning and ending energies. We know that energy is conserved, so next we can set the two energy equations equal to each other. And then fourth and finally, we can just solve for the unknown variable. So first, let's identify the types of energy. We see that the rock starts with an initial height of 5 meters off the ground, so we know at that point it will have all potential energy. Remember, before this rock is dropped, or as soon as the man lets go of the rock, it's going to have no velocity, so it will have no kinetic energy. Now as that rock moves down, it's going to be losing potential energy, gaining speed, and picking up kinetic energy. So we know the second type of energy will be kinetic. A simple way to help you out with step 1, if there's a spring involved, there's going to be elastic potential energy. If the object is traveling a height off the ground, there is going to be gravitational potential energy. And if the object is moving with a velocity, if they're asking for velocity, you know it has to be kinetic energy. So step 2, we want to have a snapshot at the beginning and at the end. So the snapshot in the beginning, we see it's all potential energy, and the snapshot at the end, it is all kinetic energy. Remember, we're looking for how fast it'll be traveling when it hits the ground. So we're looking for that final snapshot right before it hits the ground. So next we can set those two energy equations equal to each other. We know the starting energy is equal to the final energy. There's no work being done in the system by any external forces, so we do not need to account for that. We know the gravitational potential energy is equal to the kinetic energy. So we know mgh equals 1/2 mv squared. And now we can plug in numbers and solve for v, the velocity. So now I want everyone to try this. So plug in all the variables they give us, and now let's solve for v, the velocity. Here's another example for a conservation of energy problem. A Nerf gun has a spring constant of K equals 100 newtons per meter and is stretched back 0.05 meters when loaded. What is the mass of a foam dart that is shot out with a velocity of 3.53 meters per second? So I want you guys to try to follow these 4 steps, and there will be a question on Edpuzzle where you can type in your answers for these 4 steps. I know the solutions are on the next 2 slides, but please do not look ahead just yet. Try to solve these for yourself, and then you can double check against what we have written down the next couple slides. Here we have some of this example worked through. So step 1, we identified the 2 types of energy. We saw it was elastic potential and kinetic energy, right? We saw a spring, so right away we said, okay, elastic potential. Now they gave us a velocity, so now we know it must also be kinetic energy. What type of energy is at the beginning and the end? Well, in the beginning, right, the spring is stretched back 0.05 meters. And at the end or end snapshot is when it's moving with a velocity of 3.53 meters per second. Now we can set those 2 energy equations equal to each other. So we have 1/2 kx squared equals 1/2 mv squared. And then we can substitute in the variables that we know. We can substitute in the value for the spring constant, x the distance stretched, and also v for the velocity. And next we can solve for the mass, and we will get 0.02 kilograms. So here's a quick summary of conservation of energy. We know that energy is never created or destroyed. It can only change the form that it is in. If positive work is done on a system, it will increase the final energy. If negative work is done on a system, it will decrease the final energy. We will have some problems we can do in class where we will add work into the system. We can see what happens to the total energy.